All right, so for this next main chapter here, chapter 4, we're going to begin with a little bit of algebra review here, section 4.1, and look over exponential functions. Okay, so a little bit of algebra review here, discussing the properties and how to graph an exponential equation. Now recall. All right, recall from algebra here. Exponential functions with a base a, where a is greater than 0, all right, our base a has to be a positive value, have the form of the following. Have the form of f of x equal to this base a raised to the x power. So our variable of interest, our input, is the exponent of this term, where we have a real number base of a greater than 0. So our base is defined. Our input variable is x. Now, regarding this function here, the graph of the curvature of an exponential equation can depend on what the value of a could be. And again, a has to be positive. A has to be greater than 0. X can be any real number, but a has to be greater than 0. Okay, so for this function f of x, or f of x equals a raised to the x power, if a is greater than 1, if a is a real number, a real positive number that's more than 1, strictly more than 1, then in that case, we have what's known as a growth function. Okay, if a is greater than 1, then we have what's known as a growth function. So like say, for example, f of x equals 2 to the x, or 2 raised to the power of x. Here our base is 2, which is greater than 1, meaning if we were to graph this function of 2 to the x, we will have what's known as a growth function, an upwards curving function, right? An upwards type of function. All right, so let me do a quick, just a little quick drawing of what would that be. So growth function means that we have an upwards curve. Okay. Meaning our function exponentially grows as the value of x gets bigger along the x-axis here. But we're going to have a decay function. We're going to have a decreasing function. Oops. If our base a here is still positive, but falls between 0 and 1. All right, so if we get a proportion, a decimal number as our base between 0 and 1, then in that case, we have what's known as a decay function. Okay, and a decay function is pretty much the reciprocal of what we see in this type of curve. So instead of our function exponentially growing as x gets bigger, our function instead will be exponentially decaying, getting smaller and smaller as x gets bigger and bigger and bigger, and usually has like a downwards curve like this. Okay, so a greater than 1, exponentially growing function. A between 0 and 1, a decimal number between 0 and 1 as our base. Our function is exponentially decreasing. Okay, but notice again, this is strictly greater than 1. This is strictly greater than 0, but strictly less than 1. What do you suppose will happen if our base a here, oops, I forgot to make a little example. So like say an example of a decaying function would be like say f of x equals 1/2 raised to the x power. Okay, so here our base is a. Our base of a is 1/2, which is greater than 0, or less than 1. All right, so this type of function will give us this decreasing exponential type of graph. But what if our value of a, what if our base was exactly 1? If our base is exactly 1, well, let's see what happens. If our base is exactly 1, then our function of x will be defined as 1 raised to the x power. 1 raised to the x power. And again, recalling from algebra, 1 raised to any number, 1 raised to any value of x is just what? Just 1. Meaning if our base is a, then we just have a constant horizontal line crossing 1 along the y-axis. Oops, constant. So here we would just have a constant horizontal line, right, crossing at y equals 1. Okay, so mainly we're going to be focusing when it comes to exponential functions, we're going to be focusing on those with bases greater than 1 and those with a base between 0 and 1. In fact, let's look at these two and graph them in a bit more detail here. Right, just a little rough sketch of them. Let's actually graph those two functions. Let's see the front bottom here. Now make a new page. Okay, let's make a new page. And let's graph these two functions that we stated above. Let me get some graphing paper. All right, so for this first example, let's graph that first function f of x of 2 to the x. So again, here our base is 2, so we know it has to be an upwards growing exponential function. Now, to graph an exponential function, we had to set up a table, okay? There's no quick way in graphing an exponential function when doing it by hand. You gotta set up a table, plug in values for x, graph those points on a xy plane, then connect them with a curved line. Okay, so let me set up a table here. So here we are gonna have x, I put a little x, and here we're gonna have f of x. Again, f of x is 2 to the x. Okay, so just graph some lines here. Okay. All right, so let's do it for the following values. Let's graph this function using the following inputs, using the following values for x. Oops. All right, let's do about 7 points here. -3, -2, -1, 0, 1, 2, and 3. That should be good enough. All right, so now we want to, so just like graphing a function, we now want to, I just want to evaluate this function at these points that we have stated for x here. So we're going to have f at -3, meaning just plug in -3 into this function for x. So 2 raised to the -3rd power. Right, so 2 raised to the -3rd power. Which recall, that would be similar. If you want to make this power positive, then that would be similar, just be equivalent to taking 1 over 2 to the 3rd power, which gives us 1/8. Okay, recall to make a negative power positive, just flip it over, flip the base that is connected to over, take as reciprocal. Okay, so now let's plug in -2, so f at -2, 2 raised to the -2, that's going to give us 1/4. Okay, then we have f of -1, so f at -1 gives us 2 raised to the -1 power, which is just 1/2. And then we have 0, f of 0, anything raised to the 0 power is just equal to 1. right? And then 1, oops. What did I do that? What is that? That's weird. So f at 1, that's just 2 to the raised to the first power, which is just 2. And then we have 2 squared, f of 2, 2 squared, this is 4. And then lastly, 3 squared, not 3 squared, 2 to the third power. F at 3 is 2 to the third power, which gives us positive 8. Okay, so now we graph these 7 points on the XY plane. So let me draw an XY plane here. So let's see, 1/8, 1/4, 1/2. 8 is a maximum that we found. Okay, no negative numbers. All right, so let's see. So this will be 0. I'll go by ones along the x-axis and y-axis. Okay, let's graph these points. So -3 and 1/8, that'd be really close to 0. So it is around here. All right, -2, 1/4, that is still pretty close to 0. So it's around here. And -1, we have a half, so halfway between 0 and 1 here. Okay, so notice that for negative values, it's growing a bit slow. And once we pass 0 here, where at 0 we got 1, so at 0 we have 1. But once we pass 0 and start plugging in positive values, our output grows at an exponential rate. It grows at a fast rate here from one value of x to the next. So now at 1, we have 2. At 2, we have 4. And then at 3, we have all the way up to 8. So 4, 5, 6, 7, 8. It's around here. Okay. And then we connect these dots, these points. And there we see that upwards. Oops. There we see that upwards. What is it? Sort of telling that upwards curve. So here we're a function of x, where f of x is 2 to the x. All right, so there we have our growth function. Okay. Whereas in the second example that we had above, when the base value is between 0 and 1, it's a decimal number between 0 and that's going to give us almost the opposite of what we see in this graph here. Okay, so for the second example, let us graph f of x, where f of x is 1/2 to the x power. So here our base is 1/2. All right, so this should give us a decaying function. Okay, so once again, let's set up a table here. We have x and f of x. F of x is 1/2 to the x power. Make some more space in between here. Okay, put some space there. All right, so let me set up a table once again. Oops. Okay. All right, and just like we did before, let's use 7 values here. Let's use the exact same values that we used for the previous table. So this is -3, -2, -1, 0, 1, 2, and 3. Okay. All right, so then 1. All right, so once again, evaluate our function at these points. So f at -3, or in other words, 1/2 raised to the -3 power. And again, if we want to make that negative exponent into a positive, flip the base. Take the reciprocal of the base, which changes the sign of the power. So this will be equivalent to 2/1 to the third power, which gives us 8. Okay. And then we have f at -2. All right, so 1/2 raised to the -2 power gives us this equivalent to 2 squared, which gives us 4. All right, then f at -1, 1/2 raised to the -1 power gives us 2. And then f at 0, again, anything raised to the 0 power is just 1. And then f at 1, 1/2 raised to the first power is just 1/2. F at 2, 1/2 squared gives us 1/4. And then lastly, f at 3 here, 1/2 raised to the third power, 1/2 times 1/2 times 1/2 gives us 1/8. So pretty much the opposite of what we saw here. In this case, we started with, where in the previous example, we started with decimal values when we had negative inputs. But as x got bigger, 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 when we headed towards positive infinity here, the values of our function were growing towards positive infinity. Okay, but in this case, from negative infinity, they start off pretty large. But as x heads towards positive infinity, the values of our function gets closer and closer to 0. Okay, so the opposite of what we see from the previous graph. Okay, so once again, let me graph this function here. So what's the maximum? Maximum is still 8. Pretty much the opposite of what we see from the previous graph here. Okay, so once again, we'll go by 0, by 1, 0, 1, 2, 1, 2. Okay, so first point that we have is -3, 8. So -3, 1, 2, 3, 4, 5, 6, 7, 8. 6, 8. Which is double check 3, 4, 5, 6, 7, 8. -3, 8. Then we have -2, 4. -1, 2. And then 0, 1. But now as we head towards the positive side of x, at 1, we got 1/2. At 2, 1/4. And then at 3, pretty much almost right at 0 here. Even let me draw it. There we go. Okay, and so here we have this decaying function of x. Again, this function of x is 1/2 to the x power. All right, so here we have a decay exponential. All right. So again, this is just a little quick review of an exponential functions regarding the properties. Again, exponential functions have the formula a to the x, where a has to be a positive number. X can be any real number, but a has to be positive. Is a strictly greater than 1, then we have what's known as a growth exponential function. If it's between 0 and 1, then we have a decay function, meaning our function is decreased exponentially as x gets bigger. And if a equals 1, then we really don't have an exponential in that case. If a equals exactly 1, then we just have a constant horizontal line. Okay? And to graph these functions, if we want to do it by hand, we have to set up a table and try to set up at least 7 values, and that should be good enough. Okay? And actually, let's visualize these two graphs in our calculators. Okay, so let's go to our calculators and let's visualize these two graphs at the same time. All right, so here we're going to have y equals 2, oops, can't use the keyboard, 2 to the x. And then parentheses, make sure if your base is between 0 and 1, use parentheses. So parentheses 1/2 raised to the x. Okay. And if we're going to set up our tables for these two functions, we call it to set up a table on these calculators. We go to second graph. I have to do this on the app. I have to change this This first column, 2 inputs. And then let's pretty much plug in the same numbers that we use in our example. So -3, comma, -2, comma, -1, comma, 0, comma, 1, 2, 3. And close with the curly brace. Enter. All right, and there we get those same values, except in this case, we get them in decimal form. So 1/8, so for 2x, we get 1/8, 1/4, 1/2, 1, 2/4, For our second function, for 1/2 x, for 1/2 to the x power, we can start off with big numbers, 842. But as x is bigger, we're heading to the decimal values, 1, 0.5, 0.25, and 0.125. Okay, let me set up my window here to get a very clear picture. I don't know why the default numbers are so large. That's way too huge. So let's do -2 for the y minimum. Let's do 15 for the, oops, that's an x, my bad. Let's do -10 and 10 for the x values. And then for the y values, let's do -5 and 15 for the window. Graph, and there we get those two functions. Again, our blue graph here, that's our exponentially growth function. So here we have 2 to the x, which again, it gets much larger, larger, larger as we head towards the positive side of x, as we head towards the positive infinity. But then our decay function here, which is 1/2 to the x power, we start off large, but as x gets bigger, as x heads toward positive infinity, this function gets closer and closer to 0, but never crosses 0. Okay? The base exponential function of a to the x can never be less than 0. All right? So that's a little review here of exponential functions. And we'll do one more part with some applications of exponential functions that we have seen before from your algebra classes.